Okay, in this video I'm going to continue on my tutorial series on thermodynamics and statistical mechanics by taking a bit of a diversion. So I'm going to prove the binomial theorem. This is something which has scared the daylights out of me for many a year. So I don't know, perhaps you feel the same right now. So hopefully at the end of this particular video you will no longer have the daylights scared out of you. Okay, so right, where do we start? We start with the definition of a polynomial. A polynomial involves, it's an expression that involves addition, involves subtraction, it involves multiplication, it involves exponents, but no division. And more often than not we see that it is exponents. And more often than not we talk about a polynomial as a truncated power series. But I won't go into that, but it's polynomials in many respects are usually written as a truncated power series. Anyway, but what is a binomial? Well, what does bi mean? Bi means two. So a binomial is a polynomial of how many terms? Two terms, i.e. A and B. So a binomial is a polynomial of two terms. So it's basically an expression which has two terms, and the mathematical operators are plus, minus, multiply, or some sort of exponent, but no division whatsoever. And if that's the case, then you have a polynomial, and a polynomial of two terms making a binomial. So what is this binomial theorem about? The binomial theorem is is a theorem for describing what happens when you multiply a binomial by itself. So let's give an example of binomial. A plus B is a binomial. Why? Well, what's the exponent? Is there an exponent? Well, the answer is yes, the exponent is 1. Is there addition? Yes. Is there subtraction? No. But there could be subtraction. That would also be a binomial. Is there division? No. That could be multiplication. That is still a binomial. But let's talk about it when it's A plus B, we'll say, to some exponent. So what happens if I multiply A plus B to the exponent of n? The answer is that you get this really hairy expression where you have initially you've got two indices. You have this weird thing here called n choose k. You have a to the n minus k, and then you have b to the k. Now that's probably the main reason I never liked the binomial theorem, because I just didn't know. Probably the main reason I didn't like the binomial theorem because I don't know what n choose k means. What is n choose k? Now, if you've been watching my videos so far on thermal physics, you'll know what n choose k is, because that is the multiplicity function, and we've been using it so many times. But I won't talk about that yet, because I'd like this to be kind of a standalone video. So, like I said, the binomial theorem is used when you multiply binomials together. So let's look at a plus b to the 0th power, or multiplying it by 1, let's say. Well, the answer, or by 0, to get to the power of 0, let's say. So the answer is, well, it's 1. Now let's multiply a plus b to the power of 1. Well, then we get a plus b. Then we take a plus b to the 2nd power. So that's a plus b squared, like that. And we know the answer is a squared plus 2ab plus b squared. Now, just while I'm here, it's actually not as simple as that. It's actually a squared plus ab plus ba plus b squared. And because ab is equal to ba, we get this 2ab. But this that's called, if that holds, it's called commutative. C-U-M-M. How do you spell that again? C-U-M-M. Oh, commutative. C-O-M-M-U-T-A-T-I-V-E. Commutative. Now, not all things are commutative. If you're talking about quantum mechanics, most functions don't commute. But anyway, that's just an aside. So we get a plus b squared. Now, what if we get a plus b cubed? I'm not going to write. I'm not going to do it. I'm just going to give you the answer. So it's a cubed plus 3a squared b plus 3 ab squared plus b cubed. So I think hopefully you might see now why I don't like to write a plus b squared like that. I'm going to rewrite a plus b squared as follows. A plus b squared as a squared plus 2ab plus 2ba plus b squared. Now look what I've written so far. Surely it seems that there's some sort of a pattern. Now you mightn't know what the pattern is, but there definitely seems to be a pattern. Where, like, let's say, look, we have 2 and 2, 3 and 3, 1 and 1. Alright? We have A, B, B, A, A, B, B, A. And the power seems to be dropping and dropping, or raising and raising, depending which way you seem to be going. So there's definitely some sort of, or some form of a pattern. So I'm going to show you what the pattern is. So let's take the cubic equation. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, it might be difficult to do this with two colours, but we'll see how we get on. So, let's look at the powers of a. The powers of a. So we have, let's say a. So we have a cubed power. We have a squared power. We have to the first power and to the 0th power, because a to the 0 is equal to 1, which is exactly what we have in here. Okay? So it's going 3, 2, 1, 0. Now what about b? Let's write b on top. We have b to the 3rd power, to the 2nd power, to the 1st power, and then of course to the 0th power. So let's call all the indices for b, we'll call them k, and all the indices for a, we'll call them n. So n goes from 0 to 3. Sorry, if n goes from 3 to 0, k goes from 0 to 3. Or, if k goes from 3 to 0, n goes from 0 to 3. Alright? So we can see that there's definitely some sort of relationship between n and k. They seem to be swapping in value. So, it's looking, if you look at this, you can rewrite that equation as a to the n minus k times b to the k. Because let's say that n was equal to 3. Well, then it would be, and let's say it would be, yeah, well, look, I'm just going to, you can probably accept that. I don't need to go any further. You can probably accept that. If you look at this formula here satisfies that. Okay? If you look at it harder, you'll probably come up with it in your own head. But what we're missing is the coefficients, or are the coefficients. Namely, we had 1, 3, and 1, 1, 2, and 1, and so on. We're missing those coefficients. So, how do we do that? Well, once again, it's found by using a pattern. So let's look at the pattern. Let's write out what we've gotten so far. So we had 1, we had a plus b. Next, after a plus b, we had the square. So we had a squared plus 2ab, and then we had b squared. And then we had the cubic equation. So it's a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, why am I writing it that way? You might say, well, that makes no sense. Well, you may have heard of Pascal's triangle, and if you have, you know why. So, what I'd like to say is that at some stage, whenever binomial theorem was being devised, somebody had to sit down for days, months, years perhaps, and look at this. Because you don't come up with these ingenious formulae just by, you don't just look at it once and see the answer. So if you as a student haven't seen where this comes from just by looking at it, well, don't be disheartened, because you'd be under no illusions that somebody had to break their heart in order to come up with this particular formula. So eventually, most likely what happened was Pascal's triangle was found, and you also had somebody looking at the binomial theorem and found out that the coefficients on the binomial theorem were on Pascal's triangle. So anyway, so let's look at the coefficients. We have 1, 1, 1, 1, 1, 1, 1, 1. We have, and then we start having 2. We have 2 in the center here. Then we have 3. So you can see, if you build up Pascal's triangle, you see the coefficients start getting bigger and bigger and bigger. So I'm going to show you how Pascal's triangle, what it actually looks like. So I'm going to write it. It's can be tricky enough to write. Like I said, it can be tricky enough to write. Pascal's triangle, and it builds up. So this would here be 4, 1, this would be 6, this would be 4, this would be 1. Now, I've written Pascal's triangle, or the first few entries. Can you work out what the pattern in Pascal's triangle is? Well, each entry, or each element, is the sum of the 2 previous entries. So 3 and 3 make 6. 3 and 4, 3 and 1 make 4. 3 and 1 make 4. 2 and 1 make 3. 2 and 1 make 3. 1 and 1 make 2. And it goes the whole way down. So somebody realized that when they wrote down the different the different binomials to different powers, they realized that when they arranged them one on top of the other, they found the coefficients turned out to be the same coefficients that are in Pascal's triangle. So Pascal's triangle gives the coefficients for your binomial theorem. Alright, so far what we've seen is that if you look at the powers on our binomials, as you increase the power, you get the formula a n minus k b to the k, where n is the indices or the powers, the exponents on a, and k is the exponents on b. And we have our binomial is a plus b to the n of some form like that. And then in order to get our coefficients in here, we use Pascal's triangle. So is there any way to actually get these coefficients in another way? And the answer is yes. So Pascal's triangle can be gotten from n choose k. So this means n choose k. That's how you read it. The number of ways of choosing n elements from k. To be honest, I can almost never. It's how many ways you can choose k elements, k from n. So k is always smaller than n. So you might have, how many ways can I choose one element from 3, or 50 elements from 100 elements? Alright, and n choose k is just another formula. It's n factorial over k factorial n minus k factorial. So anybody do my thermodynamics videos will see, of course, why I mentioned this particular formula already. So we see the Pascal's triangle's coefficients, which are the coefficients of the binomial theorem, are this n choose k. So k is always smaller than n, so the number of ways of choosing k elements from n elements. And finally, putting it all together, we have a plus b to the n is equal to the sum from k is equal to 0 to n choose k, a to the n minus k, b to the k. And to be honest, looking at it even right now, it doesn't look any less daunting. But I'd like you just to listen for a moment. That I've built the formula up. I've shown you that the formula is very logical. I've shown you that this just came from writing down the different powers by plugging and chugging in many respects and seeing that there was a pattern on the powers. This came from plugging and chugging as well, I suppose, just plugging and chugging and arranging them so that somebody realized that it's Pascal's triangle. Alright? So if you understand, if you can accept that this is valid and that this is it's reasonable, and you can accept that this is reasonable, you can now forget about where they came from, if that makes any sense, and now say, right, I know that the binomial theorem is just about multiplying binomials together. That's all it is. And this is the formula. So if you want, you could have there's 3. If you put it at 3, well then k will start at 0, so the sum will be like this. It'll be k goes from 0 to 3, and that will be 3 choose 0, you get 3 choose 1, 3 choose 2, and 3 choose 3. So we'll have 4 coefficients. And we've done this one already, this cubical equation, so you'll know this will be 1, this will be 3, this will be 3, and this will be 1 as well. Okay, but if you want, you can plug them into this formula here. Alright, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad.